Recall that we say that two variables are associated when certain values of one variable are more likely to occur with certain values of a second variable. For example, it's much more likely for a 2-year-old to be 3 feet tall than 6 feet tall. Age and height are associated. In this session, we're going to look at how we can describe specifically which values of one variable are most likely given particular values of the other variable. For example, which height is most likely given a child's age. In statistics, this is called regression. Regression is a statement of a linear association that includes a description of which values of the response variable are most likely for given values of the explanatory variable. Regression requires variables that have an interval or ratio level of measurement for the response variable. There are actually more advanced forms of regression for other kinds of response variables, but we're only going to talk about interval ratio regression in this course. Regression is a very important statistical technique which provides a foundation or framework for many, many different kinds of analyses. In this session, we'll have a brief introduction to some key concepts in regression, and we'll come back to it later in the course for a more detailed look. In order to describe a linear association, we need some kind of mathematical statement of a line. We're going to use the slope-intercept form of the line, y equals mx plus b. Let's look at this example equation. Y equals 2x plus 1. If we plug in 1 for x, then what value of y will we get? 2 times 1 is 2, and 2 plus 1 is 3. So when x is 1, y is 3. We can do the same process for a variety of values of x, and get the corresponding values for y. Then we can take these pairs of x and y values and plot them on a coordinate plane, and connect them with a straight line. This is the line that is described by the equation y equals 2x plus 1. This equation is called slope-intercept because it's composed of two key pieces. The first is the slope. This is the rate of change in the response variable given a change in the explanatory variable. Sometimes it's called rise over run, or change in y over change in x. For our equation, let's see what happens to y when x goes from 1 to 3. Y goes from 3 to 7, so the change in y is 7 minus 3, or 4, and the change in x is 3 minus 1, or 2. So the change in y over the change in x is 4 over 2, which is just 2. The slope for this equation is 2. If the slope is positive, an increase in x leads to an increase in y. But if the slope is negative, an increase in x leads to a decrease in y. What happens when you plug x equals 0 into the equation? In this example, when x is 0, y is 1. For the general equation, y equals mx plus b, if we plug in x equals 0, then we have m times 0, which is just 0, that vanishes, leaving b. If we look at the graph, we see that the point 0, 1 is where the line intersects or intercepts the y-axis. Here's the y-axis and the point which they cross. This value b is called the intercept. It's the value of the response variable when the explanatory variable is 0. Now we have a way to describe exact linear relationships. Based on this equation, the explanatory variable tells you exactly what the value of the response variable is. But recall that statistical explanations are always incomplete, so we need a way of describing approximate linear relationships. Relationships where there's an overall linear trend, but where there are other things that affect the value of the response variable in addition to the particular explanatory variable that we're using. Instead of having data that fall exactly on a line, we almost always see something like a scatter plot. We'll take our linear equation to represent the mean of observations for a given value of the explanatory variable. That is, suppose we found this line was a good representation of the relationship between the two variables. Then, if we looked at a bunch of observations that all had x equals 2, we would find that the mean of all of those observations was 5. Or if we took a bunch of observations that all had x equals 0, we would find the mean of those observations was 1. So how do we find the linear equation that best describes the linear association based on data from a particular sample? We won't go into technical details about how the slope and intercept are estimated from data, but conceptually, the calculation is based on minimizing residuals. A residual is the difference between an observation and the predicted value, actual minus predicted. Another way of describing the residual is the part of an observation due to things other than the explanatory variable. Suppose we have an observation with x equals 1 and y equals 4, this green dot here. According to the equation, when x is 1, the predicted value for y, or the mean value for y when x equals 1, is 3. The difference between 3, the predicted value according to the equation, and 4, the value that we actually observed, is our residual. In this case, 4 minus 3, actual minus predicted, is 1. The residual for this observation is 1. So in finding a regression line, we add up all the squared residuals and find the line that has the smallest set of residuals. For example, suppose we look at the total body weight and height data from the University of Georgia women athletes. A good fitting line might be this solid red line here. A poor fitting line is this dashed line here. Notice how the residuals for the well-fitting line are smaller in general than the residuals for the poor fitting line. Now that we have a description of a linear association between two variables, we can use that description to make predictions about the response variable based on the explanatory variable. This is called a linear prediction. That is, the use of a linear equation to predict the mean of a response variable given explanatory variables. That is to say, the mean of the response variable for all of those observations that have the same value for the explanatory variable. For example, here we see the number of repetitions that University of Georgia women athletes can do at 55 pounds and 70 pounds. The best fitting line for these data has the equation y equals 0.78x minus 5.5. The slope is 0.78 and the intercept is negative 5.5. Notice that there is a positive slope indicating a positive association between these two variables. Suppose we wanted to predict how many repetitions an athlete could do at 70 pounds if they could do 20 repetitions at 55 pounds. We would plug 20 in for x in the equation, and that would give us approximately 10 repetitions at 70 pounds as the prediction. Or if we wanted to predict how many repetitions they could do at 70 pounds when the athletes could do 40 repetitions at 55 pounds, we would plug 40 in for x, and we would get approximately 25 as the prediction for the number of repetitions they could do at 70 pounds. Here we see the number of sit-ups that high school women athletes can do alongside their body fat. The best fitting line for these data has the equation y equals negative 0.8x plus 47. The slope is negative 0.8 and the intercept is 47. Notice that the slope is negative, indicating a negative association between these two variables. When body fat increases, the number of sit-ups decreases. If we wanted to predict the number of sit-ups that an athlete could do when they have a body fat of 20, we would plug in 20 for x in the equation, and we would get a little bit more than 30 as the prediction of the number of sit-ups that they could do. Similarly, if we wanted to predict the number of sit-ups they could do if the athlete had a body fat of 35, we'd plug 35 in for x, and we would get a prediction of about 20. Finally, here we see the University of Georgia women athlete data for body fat and height. You may recall that in this example, the correlation was very close to 0, indicating next to no association between body fat and height. The best fitting line for these data has the equation y equals 0.11x plus 11. Notice that the slope, 0.11, is very close to 0. This indicates that for a change in x, that is to say a change in height, there's very little change in body fat. If we plug in 60 into this equation, we get a predicted value of 17.6. If we plug in 75 in this equation, we get a predicted value of 19.25. The predicted body fat changes very little over the range of 15 inches, over a foot. When the regression line is nearly flat, that indicates that there is very little association between the two variables, because when it comes to body fat, the height of an athlete doesn't really matter much. There's no association. Why might we want to use a linear prediction? Well, perhaps one variable is difficult or expensive to observe. For example, it might be less dangerous for athletes to do the exercise at 55 pounds than at 70 pounds. Even though we may want to know how many repetitions an athlete can do at 70 pounds, we may ask her only to do the exercise at 55 pounds to reduce the chance of injury, and then use the linear prediction to get an idea of how many repetitions she could do at 70 pounds. Alternatively, we may want to predict something that can't be observed yet because it will take place in the future. For example, we may want to predict how well incoming freshmen will do in college based on how well they did in high school. We could use a linear prediction to identify students who might struggle some in college in order to provide them some additional support. So how good are our predictions? This depends on the strength of the association between two variables. For variables that are very strongly associated, the explanatory variable will yield a very good prediction of the response variable. But for variables that are only weakly associated, a prediction of the response variable based on the explanatory variable will not be as precise. For example, compare these two graphs for the University of Georgia women athlete. On the left, we have the number of repetitions at 70 and 55 pounds, and on the right, we have the athlete's total body weight versus their height. We can draw the best fitting lines, which would represent our prediction of repetitions at 70 pounds and our prediction of total body weight based on repetitions at 55 pounds and height. Then we can look at the residuals for each prediction. Remember that the residuals are the difference between our prediction and the actual observation. Smaller residuals indicate a better prediction. It means that our prediction was closer to the actual observations. There was less error in our prediction. Notice how the points on the left are closer to the line, that is to say there are smaller residuals, than the points on the right, which have larger residuals. Recall that we could measure the strength of a linear association with a correlation. The correlation for the graph on the left was 0.94, and the correlation on the right was 0.74. The graph on the left shows a stronger association than the graph on the right. Since variables with higher correlations, or that is to say stronger associations, give better predictions, we can create a measure of the quality of a linear prediction based on the correlation. This is called the coefficient of determination, a measure of the quality of a linear prediction. It's computed as the square of the correlation. Another way to interpret the coefficient of determination is the ratio of the explained variation over the total variation. Let's look at what that means for the University of Georgia women athlete data for the number of repetitions they can do at 70 and 55 pounds. If we only look at the number of repetitions they can do at 70 pounds, we see that the values range from 0 to 35. But we know that the number of repetitions they can do at 55 pounds can explain the variation in the number of repetitions at 70 pounds. After we find the best fitting line, we can calculate the residuals from a linear prediction of repetitions at 70 pounds based on repetitions at 55 pounds. These residuals are what is left over in the number of repetitions at 70 pounds after explaining what we could based on the number of repetitions at 55 pounds. The residuals have less variation than the original variable. This variation is what is left over after explaining the variation in repetitions at 70 pounds using repetitions at 55 pounds. The difference in the variation of repetitions at 70 pounds and the variation in the residuals is the part of repetitions at 70 pounds that was explained by repetitions at 55 pounds. And the coefficient of determination is the ratio of the explained variation to the total variation. Now, there are some things we need to be careful of when we're analyzing associations. First, when we create a linear prediction using regression, it's based on certain observed values for the explanatory variable. These predictions may not be valid for values of the explanatory variable that are outside the range used in the regression analysis. This is called extrapolation, that is, making a prediction outside the range of the observed data. We don't really know what the variables do outside of the range of the data that we have. It could be linear, or it could be different. Sometimes extrapolation doesn't even make substantive sense. Let's look at an example. Here's the equation for repetitions at 70 pounds and 55 pounds again. Y equals 0.78x minus 5.5. For an athlete who can't do any repetitions at 55 pounds, that is to say when x is 0, what does the equation predict is the number of repetitions she can do at 70 pounds? Well, if we plug in 0 for x, we get negative 5.5. But it doesn't really make any sense to be able to do negative 5 repetitions. That's just not possible. The data we have only go from a little less than 10 to about 50. So this equation isn't valid for predicting repetitions at 70 pounds when an athlete can't do any repetitions at 55 pounds. Similarly, if we were to plug in 60 for the number of repetitions at 55 pounds, we would get 41.3 predicted repetitions at 70 pounds. But the data don't go as high as 60, so we don't know whether the trend continues to be linear or if it starts to level off. Second, regression lines can be strongly influenced by the presence of outliers. Let's take a look at this example. Here we have the level of violent crime and the level of college education for a number of different states. If we calculate the best fitting line, we see that it has a positive slope, indicating a positive association between college education and violent crime. That is to say, in states that have more highly educated people, there's more violent crime. Does that really make sense? Notice that most of the data are around here, but there's this one point that's way up here. It has a very high level of education, but it also has a lot of violent crime. This point clearly seems to be an outlier. Something's going on with this point that's very different than the rest of the data. If we remove that data point and calculate the best fitting line, we get this green line here, which has a negative association. The higher the level of education, the lower the level of violent crime. That's more like what we would expect. It turns out that this point, this outlier, was very influential on the regression line, and we would never have figured that out unless we had plotted the data and seen that this point was different than the rest. So as I've said before, always plot the data. Finally, you may recall that even though we sometimes use causal language when we give a statistical explanation, I was very careful to point out that a statistical explanation is not necessarily a causal explanation. Another way of saying this is that correlation does not imply causation. Among other things, this is due to the fact that there could be lurking variables or hidden causes, as we discussed before. So if you find an association in an observational study, you first have to ask yourself, could there be something else that's causing this relationship?